Welcome back, I am Alex, and this is the AI Research Roundup. Today's paper from Papers with Code is OpenThinkIMG, Learning to Think with Images via Visual Tool Reinforcement Learning, published May 13, 2025. It introduces OpenThinkIMG, an open-source framework to help large vision language models, or LVLMs. AI models understanding both images and text learn to use visual tools. They also propose V-TOOLRL, a novel reinforcement learning framework. Reinforcement learning lets AI learn by trial and error from feedback. So V-TOOLRL helps LVLMs discover optimal tool use strategies, improving on supervised fine-tuning, which uses static, pre-labeled examples. So this OpenThinkIMG framework and the V-TOOLRL approach sound pretty promising for getting these large vision language models to really interact with and understand images more deeply. And if you want to dive deeper, well, the authors have released their OpenThinkIMG repository. It's the open source framework for this research. So in there you'll find the code for training, like for supervised fine-tuning and their V-TOOLRL method, the vision tool setup, and good instructions to get started. Alright, so Figure 1 gives us a nice overview of this OpenThinkIMG framework. The top part shows how it works during inference, when it's actually using the tools. A user provides a query and an image, which go to the large vision language model backbone. This backbone then figures out what tools to use, like OCR or zooming, via a tool controller. The tool outputs then feed back into the model for more reasoning. The bottom part of the figure illustrates the V-TOOLRL training process. It starts with a cold start phase, where a base model is trained using supervised fine-tuning on pre-generated examples of tool use, creating an initial policy model. A policy model, well, it's essentially the AI strategy for choosing actions. Then, in stage 2, this policy model learns through reinforcement learning, performing K-turn rollouts, which are sequences of interactions with the visual tools, and getting feedback to improve, ultimately producing the final, more capable model. Okay, so we've seen how the OpenThinkIMG framework is structured and how the V-TOOLRL training works. Now, Table 1 gives us a closer look at the actual visual tools that the large vision language model can use. It lists tools like GROUNDINGDINO for text-driven object detection, SAM for precise segmentation, which means, accurately outlining objects, OCR for text extraction, and others for cropping, pointing, drawing lines, or even zooming into subplots. Each tool has specific inputs, like an image and maybe some coordinates or text, and produces outputs like bounding boxes, text, or an annotated image. This diverse toolkit is what allows the model to interact with the visual information in so many different ways. Alright, so after seeing the variety of tools, Figure 2 here really shows us the payoff. It compares the performance of V-TOOLRL on a benchmark called the CHARTGEMMA test set. Part A of the figure lines up V-TOOLRL against other models. You can see V-TOOLRL hitting 59.39% accuracy, which is quite a jump compared to other open-source models like Taco8b and CogCom13b. It also stacks up well against strong closed-source models, even beating GPT-4.1. Then Part B breaks down how each part of their training contributes. The base large vision language model, Quinn Base, starts at around 29.56%. After the cold start phase, using supervised fine-tuning, it improves to 45.67%. But the full V-TOOLRL, with its reinforcement learning, pushes the accuracy all the way to 59.39%. This really highlights the significant gains from their reinforcement learning approach, especially when compared to a text-based reinforcement learning method that only got 51.63%, showing that integrating visual tool feedback is key. Alright, so we saw V-TOOLRL performs really well. Figure 3 now digs into how it learns over time during the training process. Part A is interesting. It shows the average number of tool calls per sample drops quite a bit as training goes on, from over 0.6 down to around 0.1. This means the model becomes more efficient, learning to be selective about using tools. Then, Part B shows that the completion length, which is the length of the model's output in tokens, or small pieces of text, actually increases, suggesting it's developing more detailed reasoning. Finally, Part C clearly shows V-TOOLRL in orange, achieving higher reward accuracy in learning quicker than the text-based reinforcement learning baseline in blue, reinforcing that visual feedback is indeed very helpful. Okay, so after looking at how V-TOOLRL learns efficiently, Figure 4 gives us some qualitative examples, basically side-by-side comparisons showing how it reasons differently from a model like GPT 4.1. In the top example, a pie chart question, V-TOOLRL uses tools like zoom in subfigure to focus on the relevant part of the chart, and then OCR to extract the specific text data. Similarly, the bottom example, with a line graph, shows V-TOOLRL using point and draw vertical line by X tools to mark specific data points and draw visual guides on the image. This structured approach, breaking the problem down with the tools, helps V-TOOLRL arrive at the correct answer, whereas GPT 4.1, which attempts to interpret the image directly, sometimes falters on these complex visual queries. Those examples really show how V-TOOLRL tackles visual problems in a more structured way. Overall, this research demonstrates that teaching AI to actively use visual tools rather than just passively observing images significantly boosts its reasoning capabilities. It's a promising step towards AI that can truly understand and interact with the visual world around us. Well, that's all for this AI Research Roundup. Thanks for tuning in. I'm Alex.